So, following from there, distribution of sampling mean, right, distribution of sampling mean, as I said. Now, you can algebra we can understand simply we can understand the algebra easily. It is like this, like supposing I have x1 bar, I said is a mean of n samples, which will be, let me call it as x11 plus x12 plus x13. These are the samples up to x1n divided by n. x2 bar would be simply x21 plus x22 plus x23 etc., x2n divided by again n. And if I sum all of them up, that is sum up x1 x1 bar, x1 bar, x2 bar plus x3 bar etc., and divide by m of them, xm, because I said m number of times I have repeated this experiment. So, this will be my overall x bar. Now, this can be expanded, and what it would be? It would be simply x12, x11 plus x12 etc., and this will be then divided by n into m, because each one of them is, this will be x21, x23 etc., plus x2n divided by n. So, this will be sum of all this x12, x21, x22 plus x m1 plus xm2 etc., divided by n. That means, large number of them divided by total number of my observation, which will be actually, it is a simple n into m, and I have got total n into m number of data divided by n into m. That means, it will be the true mean. So, mean of the sampling mean is same as the mean of the population. Sampling mean of sampling mean, mean of the means is population mean. That is one thing we understand, right. Standard deviation one can derive and show, standard deviation one can derive and show, right. Standard deviation one can derive and show that standard deviation is actually given by this formula, which I have just written straight away. For example, you determine for n is the sample size, S is the population, estimated population standard deviation. If it is known, well known, then we write it like sigma square by n, and this is sigma of n, where this stands for standard deviation of the sampling mean with n sample size. So, you can see that supposing I have n equals to 4, my sampling mean, standard deviation of the sampling mean will be population standard deviation divided by 2. If I take 3, it will be under root 3. See, if I take 3 and take their mean, the standard deviation of such means will be population standard deviation divided by under root 3, because I am squeezing down, reducing down. So, this you can again prove. Same manner I have done it for mean very quickly. You see any statistics books, you will find it out, but you can prove it also. So, more number of samples you take, you are likely to be closer to this value. Supposing I take still larger number of sample, very large number of sample, infinite number of samples, and find out their mean, standard deviation will be 0, because every time the mean will be here. Supposing I take 100 or 1000 and find out the mean, so the value will be very close to this. Next time I do again, I will find value close to this. So, if it is theoretically infinite, it will be standard deviation will be 0. So, that is why inversely proportional to n. If n equals to 1, then it will be same as the population itself. So, do you understand that? So, if you increase the number of samples, so in situ testing also we can adopt these kind of principles. This is called stage to stage formula when I am doing it from small samples. So, number of samples I can do it that way. Now, just to go to example that this is what we use in concrete technology or concrete practices, it says that acceptance criteria of concrete is, it says that 4 non overlapping consecutive samples and their mean should be greater than FCK plus 0.825 sigma. FCK plus 1.65 sigma is the mean, and mean plus if this mean plus maximum variation will be mean plus, mean minus, sorry, on the lower side 3 sigma, 99.9% of the time the least value. So, this is if my mean is this, standard deviation is this, my no cube strength, sample strength or cube strength should go below this. If I am taking mean of 4 samples, standard deviation becomes this under root 4 and this also becomes under root 4, right. And if instead of taking 99.9% of the time, if I take it to be 95% of the time, my strength should not be falling below this. My strength, the point is 95% of the time my mean is this. The least value 95% of the time my cube strength should be greater than FCK plus 1.65 sigma minus 1.65 sigma, 95% of the time, right. Now, supposing I am taking mean of 4 samples, then this is sigma under root 4 and this is sigma under root 4. So, 95% of the time the 99.9%, but 95% I am taking then 1.65 sigma. So, what I am saying 95% of the time mean of 4 samples should be greater than thing 95% of the time. 95% correspond to 1.65, 99% corresponds to 3 sigma, 99.9. So, if you calculate this out, this comes out to be 0.825 sigma, because half of this root 2 divided by 2 and this is also, it will come out to be. So, if this is what it should be. That's why my acceptance criteria is given like this. You can also derive yourself the same thing. Just look at this. Mean of 4 samples should be greater than this FCK plus 0.825 sigma, 825 sigma, because FCK plus mean is FCK plus 1.65 sigma minus 1.65 sigma divided by 4, because this is mean minus. So, 95% of the time this should be greater than this value. So, that is why this 825 sigma comes in. Okay, forget it, this part I am not interested in telling you in this class, right. So, this was earlier starting point of the code, now they have modified it, but that is not, I am not interested in this. So, all that I am trying to say is this concept is used in acceptance criteria also. Example I have just shown you. So, this if you see it, you will see in the code it gives you that mean of 4 samples should be greater than this or something FCK plus something. That is been put in arbitrarily, because there may be controversy related to sigma. So, code has to do the legal issues also. So, they have put in some value FCK plus 4 or something 3, it should be 90 above FCK plus 3 for acceptance. So, if you see this concept is applied in acceptance also, alright. So, I think that is it. So, this also says individual strength result should be greater than FCK minus 3. You can be less than FCK also, because M15 does not exist for M20 FCK, whatever it is, this I am not interested. So, this part I am not interested, I will not solve the problem either, but I think I have given you the concepts. So, number of segment therefore or number of samples is related to that. Supposing I test 10 of them, then my standard deviation would be sigma under root 10. It means that I will be closer to this. Now, if I test 16 of them, I will be still closer. No, I will be closer to them. That means my error, maximum error, if I assume 99.9% of the time, will be plus minus 3 of this. Maximum error will be plus minus 3 times sigma under root 10 or plus minus 3 99.9% of the time sigma under root n, if I know sigma very well, which means that if I increase number of samples, then I will be, my error will be less. Error is plus minus, you always whenever you do experiments, you say mean or results plus minus some value. So, this error is given by this formula 3. So, if I have more n, error will be less, that is the idea. So, then this particular case of that segments that I was talking about, the tunnel lining segments that I was talking about. So, these concepts we could use. And number of tests required to obtain mean true results with an error E is given by, confidence level is given by this formula, where Z is 3 for 99%. If you do not have the population unknown, the standard deviation is unknown, then you determine populations, I mean the standard estimate standard deviation through small sample test, and then you have to use what is called t test. So, error is E is equals to Z, Z is that 3 value for 99%, sigma population divided by under root n, this is the error. So, n you can find out will be equals to E square, I mean this Z square, Z into sigma p divided by E square. So, you want to reduce down E, low E means more n, low error means more n, because from this formula it follows, because I said that error is plus minus for 99% 3 sigma under root n. For any other value 95% this will be 1.65, Z will be 1.65. So, Z sigma under root n. So, therefore, if you want to find out n using this formula, you can find out. When sigma p is well known, standard deviation of the population is known, for cube strength population let us say, for in situ strength population I know, or rebound MR if I know it well, then I can use this formula. But if it is not known, I have to determine it first, then I use this formula. So, do a small number of tests and find out what is the standard deviation, but your standard deviation will not be true population standard deviation. Therefore, you have to use what is called t distribution, students t distribution, which is meant for small sample size. So, t values will be obtained from table depending upon how many, what is the size of your n for determination of S, and similarly you can find out n. So, number of tests is determined based on this depending upon how much error you need, but there is another point, more the number of tests, cost of testing will be more. So, you have to have a compromise on the cost and accuracy. You want higher accuracy, you have to do more tests. You want higher accuracy, then you have to spend more money. But if your budget is limited, then obviously you compromise. So, number of test segments one can determine. For example, we found out standard deviation was 3 MPa, mean strength 54 MPa, we determined. So, number of tests required to obtain mean true result within 5% error with a confidence levels of 99%. In this particular case of the segments I was talking about, the tunnel lining segment worked out to be 15 in this particular. So, 15 segments were tested for randomly for various kind of tests, to wherever it was, or similar kind of concepts you can apply elsewhere to in order to see your accuracy. So, here accuracy was more important, cost was not a factor. Some cases cost would be a factor, and there you have to take it, right. So, that is what it is. So, we collected visual inspection records in a systematic manner according to suggested format and color coding, which I told you in the last class, that we looked at the crack, marked them double red to green color. Double red was maximum size crack, green was the minimum size crack, and so on. So, that is how one can determine this, right. Okay. So, number of test locations, let us look at it now. So, in case of general structure, this was a case and I showed you an example how we find out the number of tests required. It is not arbitrary. You go to a consultant who does testing, they would suggest as many number of tests as possible, but that should not be the case. It should be done depending upon the requirement. I think I must be having another slide related to the number of tests. Let us see if I have, yeah, this first I will talk about this one, then I will go back again, the location part of it. Cost of test will include actual cost of test, because you have instrument cost of the, like they would like to recover the cost of the instrument, the whoever is doing it, the labor cost, setting up cost, etc., etc. The cost of damage to the structure, if there is any, for example, you do a code test, you have to fill it back. So, more number of tests you do, more damage to the structure. So, some cases there is damages, so where there is no damages, this cost is 0, but if there is a damage, then that is. Then cost of disruption. If you are stopping the activity, not allowing traffic to pass through the bridge or not allowing the class to occur in a classroom, there is a disruption cost involved. So, therefore, the total cost of ith type of test, for any test this time would be different cost. So, the total cost will be this, and for all n type of tests the sum total will be C I into N I, right. The total cost should be minimized for a given budget. So, you keep that B, then you decide on accuracy and say compromise between the two, right, compromise between the two, because accuracy has to be maximized. It is a kind of a goal programming situation. You have cost has to be minimized and accuracy has to be maximized, right. More the number of tests, cost goes up, but accuracy also improves, error reduces. So, that is how we decide number of test location, right. Okay. So, now we come to choice of test location, number of test location we have already talked about. Now, then we can find out the standard deviation from CV values from literature if I do not have any idea. For example, coefficient of variation is nothing but standard deviation divided by mean. So, it is given for very good concrete, the dark line is in situ concrete where CV will be higher and dotted ones are standard laboratory samples. Poor concrete, so if you know the grade or mean strength, then you can find out these values for very good concrete, for normal and for poor concrete, even if you do not have idea about the standard deviation, because CV is nothing but standard deviation divided by mu or mean. So, SD divided by mean. So, percentage is given, so you can get an estimate. This is from a book by Bungie and Millard. They would have done it for in UK, they would have done it. So, from that it is that way, right. So, the CV is one can find out CV in this manner. So, standard deviation in mean one can find out, right. So, rough idea you can get it, but then you can do a small number of tests and then establish the standard deviation yourself and use t test, that other formula, stage to stage formula which I have given you with t, that you can utilize. Okay, so, that is what it is. Now, this is the cost aspect that I was talking of. So, total cost should be within the budget. Then test locations. Now, I said concrete strength varies systematically in concrete. For example, if you see typically for a column, strength at the bottom is, if I assume it to be 100%, 1 percentage variation, it is much less at the top. So, this is top, this is bottom, this is mid height, 3/4 height, 1/4 height, etc., etc. So, it is because the cement, and also with the way we construct and the reinforcement there, right. So, essentially what we will do, I will pour concrete from the bottom, maybe in 2 lifts, right, but the water cement ratio is minimal at the bottom. Cement will go most, water will come up, and reinforcement depending upon, because I may not be, like part of the shuttering I might have put in side shuttering, then I have done the casting. As it becomes deeper, tendency to compact it also, the possibility of compacting it becomes also somewhat less. So, this is from experience. Wall something like this, the slab something like this, and beam something of, column is here, this is for beam, this is for wall, because it also depends upon the reinforcement, congestion and all that. So, this is for beam, this is for column, top is bad, double layer. So, you can see that one lift, maybe something of this kind, So, typically this is what is it. So, the point that I am trying to make is, strength of concrete is not same at all heights. So, while doing sampling, you do not do it from same height at all locations, you randomize it, 1/3 from the bottom, 1/3 from the middle, maybe 1/3 from the top. If you take everything from the top, you are likely to bias your results with poor concrete. If you take everything from the bottom of a column, bottom of all the columns, you are likely to bias it towards the positive side. So, this has to be understood. Normally, these people may not understand, take care of this and just do it as it is. Then you have got, this has been also observed. Typically, if you have, supposing I am 35 grade of concrete. So, mean strength will be 35 plus 1.65 sigma, could be something of this order, depending upon the standard deviation, But then top and bottom, if you see, in case of column you might find 20 to 27, while bottom 30 to 36, wall, this is in situ I am talking of, cube strength is 40 to 43, mean cube strength, right. Mean cube strength, this is a cube, this is a grade, this is a mean cube strength, and then wall is something like this, slab something like this. So, you can see the strength in structure is much lower, much lower than cube strength, because cube is a standard cube, strength is much lower in actual structure. Besides that, this is taken care of in design, nobody has to really worry about it, because you already multiplied or divide by, multiply by 0.67 in order to take care of this, divide by 1.5 you can say, but then there is a partial factor of safety, that is also 1.5. So, first if you remember, you take column 446, you take FCK for compressive strength of concrete, that is because FCK divided into 0.67 divided by 1.5 as a partial factor of safety of material. So, basically this 67 takes care of this and something else, adverse effect of loading as well. So, all this factor put together, it has been seen that in situ strength that one can realize because of the nature of cube is tested in a standard manner, while structural loading could be different. Also, the strength variation occurs in structure. So, therefore, it has been observed actually it is about 80% of the 85% of the cylinder strength, American code. So, cylinder strength itself is 80% of the cube strength. So, 0.8 multiplied by 0.85, if you look at it, how much it will come to 0.68 or something. So, British code or Indian code, they took it as 0.67 of the cube strength, right. So, that is taken care of, but one must realize that strength that you get inside would be lower than cube strength or grade strength. You have to, interpretation has to be done, then you got to do it that way. Okay. So, this will be handy coming later on, but my point here, more important point here that I am talking about, that you select the locations randomly at all height level, and do not select the location which is vulnerable. Do not cut a core through the yield lines of a slab, because you are making it vulnerable. Avoid cutting possibly reinforcement bars. Okay. So, this is what it is, right. So, choice of location of test, as I said, concrete properties very systematically within member, and this is what again another graph shows, it was from one of the British codes, earlier British code, right. So, actual strength in the structure, top would be lower, bottom will be higher, cube strength will be equivalent cube strength you can think of, that will be lower here, higher here, right, cylinder strength and so on, and standard cube strength is here. So, this same idea is given again here. So, if you want to compare particularly, then randomization is not necessary, but take it from such place. Supposing I want to compare the strength of column, this has happened to me, this practical cases in many places, practical cases in many places. It happens that you would like to compare, supposing you don't, somebody does not want you to do actually extensive testing, just you can do non-destructive testing and tell me this concrete is acceptable in this set of columns. This has happened, in some cases it has happened. In fact, one of the flyovers here also was a similar case. Some portion was acceptable, some other portion there was doubt. So, what you do? And they say no, you do not take too many cores, already traffic is going on or the column office is on. So, I can give you only short period of time, you do non-destructive testing and find out. So, what you can do? You can compare, and if this is good and this is also belong to the same population statistically, you can say this is acceptable. If it does not belong to that population actually showing lower properties, you say that no, this is no good. you need further testing. So, comparison if you want to do, then test at the same locations both places. So, set of columns, supposing you are given that these are good columns, these are bad columns. So, you should be testing mid height for all the columns, this side and this side. Do not take from top height, bottom height, and one can bias the result. So, that such biasing should not be there. So, while comparing elements, say columns, the test hypothesis is that one set of column is as good as other one. Relative location need to be chosen in relatively same location. Same relative location should be chosen in both the set of columns, right. While comparing properties of elements, say columns, test hypothesis, okay, when it is necessary to obtain overall properties, then random selection at the top, bottom and middle you should be doing as much as possible, stratified it 1/3, 1/3, 1/3 sampling. So, that would be desirable. So, that is what how we choose location of test. So, first part was visual survey, second part was choosing the tests, and third is location and number. So, I think we have covered that part. Yes, last class I was talking to you related to crack depth measurement. Now, this can be done through, let me see if I can show you how it just, this is a simple device in my hand. I will just show you, if I can. So, this is a simple device, right, it will not come in, it will not come in. Does it come in here? No, it will not come in, may come in somewhere there. This is a simple device, maybe I will have it again somewhere. Supposing this is my crack thickness. So, this is a device, it has got a graduation, it has got a graduation. Okay, कर लीजिए, just quickly कर लीजिए. So, this is a device, for example. This device, it has got a scale, right, and thick lines like this. Some you will have one line, then one line slightly thicker, then another line slightly thicker, another line slightly thicker. So, you place the scale on that, right. Place the scale on that, then you can find out the crack width simply. This is a simple scale. There are more complicated ones. Okay. So, for example, I want to find out, if you see this scale, now this line I just match with this particular one. So, it is about 3.35 mm, right. Now, supposing zoom, and इसके ऊपर लिखने के लिए what can I use for writing here? This pen, right. Now, this is a simple, it shows how much thickness it shows, 0.35 mm. This scale you can read. Now, supposing the thickness was something like this, then I will match with this particular one, right, this particular one. You see, these thicknesses are different. So, this is different. So, this is 1.5 mm, this is 1.5 mm. So, I place the crack, place the scale over the crack. Supposing the crack is something of this dimension, place it like this, then I say the crack width is 1.5 mm. And if it is very fine, finer than even this line is 0.35 mm as I have seen, or something like that. There will be slight error. So, this is how we can find out the crack both in inches, and this is a simple scale. There are better ones of course, but this is a simple scale which one can use to find out the crack width, right. So, this is still zoom, it can be zoomed further, no, this, no, zoom, plus, right. This you can see now properly. So, this is a simple scale, and as I said, like this thickness is 1.5 mm or 1.5 mm. Accuracy would be of course depending upon, it is not very easy to make it accurate, but maybe if you put a magnifying glass, then you will see it more accurately, you can measure. For example, this is coming out to be 0.40 at the moment, as I am able to see this particular line here is 0.40 or 0.35, this line or maybe 0.35, but if I magnify it further with a magnifying glass putting error, I can see it match it better, match it better. So, this is how one can measure the cracks. So, we have seen now crack measurements. Maybe next class we will look into some of the test measurement, right. Okay.